So for our warm-up problems, we're going to be working with the same factors of C that add up to B method that we learned in the last class. So again, what I mean by B and C, or A, B, and C, is just I'm taking the coefficients of each of these terms. So our coefficient is just our lead number here. When there's no number written, you all know that we just have A is 1, B is negative 15 here, and C, or our constant, is going to be 50. So we need factors of 50 that add up to negative 15. For all the problems that we've done so far, you're going to find that A is always equal to 1. So that doesn't really come into play. All right? So B is negative 15, C is 50. Those are the two pieces we have to try to factor this. So we need factors of C that add up to B. So two factors of C that add up to B are going to be negative 5 and negative 10. How do I know? Negative 5 times negative 10 is 50. Negative 5 times negative 5 plus negative 10 is going to give me negative 15, right? Because adding a negative is the same as subtracting a positive. So the two numbers that I have here are negative 5 and negative 10. So I write it just like this: x plus negative 5 times x plus negative 10, which is of course the same as x minus 5 times x minus 10, right? All we're doing is we're taking these two numbers that we found and we're adding them to x within a set of parentheses, giving us two binomial factors, right? Same set of steps over here. We have A is 1. Again, it's always 1 for the problems that we've done so far, and that's actually what we're going to get into today, is working with problems where we don't have A as 1, okay? Here, B is going to be 2. C is going to be negative 8. So we need factors of negative 8 that add up to 2. What are two factors that do that? We have 4 and negative 2. 4 times negative 2 equals negative 8. 4 plus negative 2, or 4 minus 2, equals 2. So these are the two numbers we're working with here. We're just adding both of them to x as binomial factors. So we have x plus 4 and x plus negative 2, which is the same as x minus 2. So here you have it. We have x squared minus 15x plus 50 equals x minus 5 times x minus 10. Over here, we have x plus 4 times x minus 2. Sometimes, and I've been guilty of this myself, sometimes we don't get the right answer when we're doing this. We think that we have the right answer, but we didn't really do it through. Sometimes we find numbers that multiply to B but add up to C, so we might get it mixed up a little bit. The way that you can check this is what? Exactly, foiling. So let's take a look at that, and we're going to try to work with grids today. And I think that'll make things a little bit easier for you guys. It'll actually help you get an easier understanding of the stuff we're going to do later in class today. So if we set things up in a grid here, right, I have x and negative 10, x times negative 5. It's a lot easier to factor things from here, or not to factor things from here, to FOIL things from here once we have our factors. And that's going to give us, at the end, 4 different squares, or it makes a little bit of sense, but say we have a third term over here. We would just have 2 times 3, or the number of terms for one set of factors, or for one factor, and then the number of terms for our other set of factors. That's going to be a total number of squares. To find out what this adds up to, all you do is just add the squares together. So in both these examples, we have just binomials with x having a coefficient of 1. So x times x equals x squared. X times negative 5 is negative 5x. Negative 10 times negative 5 is positive 50. You add these up, and since there's only 3 different degree terms, right? We have our quadratic term, our linear term, and our constant term. Having 4 different squares means that only one set of like terms is going to end up getting combined. So here we have negative 10 plus negative 5 gives us negative 15x. That checks out. We got the right answer. Ta-da. All right, over here we have x squared is x times x. Negative 2 times negative 4 is negative 8. And our inner and our outer terms, right, are negative 2x and 4x. So we add these two up. 4 plus -2, as we just said, is going to give us 2 for our coefficient for b. And surprise, that checks out too. So now we're going to get into, just like I said before, we're going to get into problems where we don't have, right, where we don't have a equals 1, right? A is going to be some other integer, and I'm just giving you a bit of warning now. We're not going to do a lot of problems where A is going to be negative, because down the road you'll find out that it just doesn't come up a lot. So for now, we're going to work with a lot of problems that look like problems you've seen before, right? It's just that we're going to have some natural number greater than 1, right? So let's think for a second how we can factor something like this, right? We had the factors of C that add up to B method last time, and that seemed pretty intuitive, pretty quick, right? This is going to be a little bit more complicated, but it's going to look a lot like what we just worked with, all right? So just take a second right now and see what you come up with, see like what ideas you have in general here. I'll give you guys a few hints, and we'll see where it goes from there. All right, so here's the problem. We need to know how to factor this right here. We need to know how to factor ax squared plus bx plus c, right? Before, we were only worried about factoring this, because a was 1, anything times 1 is itself, right? So really what we're going to do, the first thing that we're going to do is we're going to take this b term right here, our linear term, and we're going to split it up into 2 different pieces. All right, we're going to use something like that C, or factors of C that add up to B method that we used before. It's actually a more general case of this, and it's going to help us solve these type of problems. It's going to help us split up B so that we can work back into that grid format that we just saw. All right, so like I said, we're splitting up this B term into 2 different B terms, right? So 2 different linear terms, and then that's going to give us 4 terms, just like that grid we had. Okay, so what we're going to do to find out what those 2 coefficients should be, B1 and B2, we're going to say, okay, we need 2 factors. We need 2 factors of A times C, right? A times C, the 2 factors of it have to multiply the same product, okay? So we have A times C equals B1 times B2, but those same 2 numbers add up to B, right? Just like before. So 2 factors that multiply to A times C, and add or sum to just plain b, right? So that b that we had is our original linear term coefficient. So let's do this in our old problem. I know this seems a little bit intense, so let's back it up a little bit. Let's couch this in the same problem that we were just working with, all right? Okay? So this is a little bit more complicated of a problem, so I think it'll help if we try to think of this in number of steps, okay? There's going to be just 3 steps with really a pre-check before that that'll help us get started with the problem and make things a little bit simpler so that we're not doing more work than we need to, okay? So like I said before, we're trying to factor 6x squared plus 15x minus 9. First thing we're going to do, our pre-check, before we do anything else every single time. I'm urging you now because I'm telling you, I've seen people just spend way too much time on problems like these when they don't go through the pre-check, okay? So what we're going to see here, our pre-check, is that we're going to pull out a GCF, right, of all 3 of our terms. So our GCF is probably pretty much always going to end up being something that's just a number, right? It's only going to be a coefficient. Why? Because as you can see here, this 9 doesn't have any variables in play there, so it's not being multiplied by any variable, meaning that we can't take out any variables, right? If we're factoring out something, that means we're taking it away from every piece there. We're reverse distributing in a way, and we're dividing it out. So 6x squared plus 15x plus 9, we're only going to be able to pull out a number, right? Our GCF has a minimum of 1 for all of these problems, but if it's just 1, that means that it's unfactorable, right? Just like we saw from earlier in the chapter. So if we're working with something like this, 6x squared plus 15x plus 9, right? Sorry if I misspoke there. If we have a problem like that, we're going to need to pull out what we have as a GCF first. And as you can see here, we can pull out a 3, and that leaves us with 2x squared plus 5x plus 3, right? 3 times 2x squared equals 6x squared. 3 times 5x equals 15x, and 3 times 3 equals 9, right? We're going to take that 3 out, and we're just leaving now for the duration of the problem, all right? We're going to come back to that. But that idea there of just pulling out that 3 means that now we're just working with a simpler problem. Now we're just trying to say, okay, let's factor this. It's got lower numbers, it's a little less scary, and I think it's going to make a little bit more sense. So like we just discussed, we said that we needed factors of a times c that added up to b. So we have factors of a times c, or 6, because that's 2 times 3, a times c, that add up to 5, right? So it's kind of hard to just guess this kind of thing. So really what I like to do is just draw a table of writing down what my possible factor pairs are, so writing down all of them, and then just seeing which one adds up to the correct amount. If none of them adds up to the correct amount, or that b term that we had, right? B right here, so a, b, c. If we have nothing that adds up to b correctly, then the best thing that we can do, honestly, is just say that it's unfactorable. There's nothing else to do. It's not your fault. Don't worry about it, okay? So here we have factor pairs that add up to 5, right? We're looking for a factor pair of 6 that adds up to 5. So our possible factor pairs are going to be what? Okay, so we'll have 2 and 3. You guys are smart. Okay, so let's go with -2 and -3. What else? 1 and 6. There's one more. We haven't heard from -1, -6. What do these add up to? Surprise, you guys picked out the first one immediately. All right, -2 times -3 is -5. We have 1 times 6, or 1 plus 6 is going to be 7. Sorry. My bad. 2 plus 3, right, is going to give us... Oh, I was right. So, 2 plus 3 is going to give us 5. -2 plus -3 is going to give us -5, and you can see that these are opposites when we have just the opposite set of factors there. 1 plus 6 gives us 7, and -1 plus -6 gives us -7. 5 is, of course, what we're looking for, so that means 2 and 3 are going to be B1 and B2 that we talked about, okay? So I know that this seemed like a lot of work for step 1, but really that's the meat of the work here, okay? So we're going to be able to see this a lot easier in step 2. All we're doing in this next step, really, is rewriting things as having 4 terms. So we needed, among some diligent erasing, all we need to do is to take those 2 terms, that B1 and that B2, or take that B and turn it into 2 different linear terms, all right? And that's going to make things easier to factor, because what we're going to end up doing is just fitting all the pieces back into our grid that we worked with earlier, and then splitting things out from there. So we have ax squared plus b1x plus b2x plus c, using the numbers that we had before. So we had a was 2, so we have 2x squared plus something linear plus something linear plus 3. And what were the numbers that we found? What did we turn that b into? We turned it into 3 and 2. Some of you are saying, okay, well, why can't it be 2 and 3, or 3 and 2? We'll actually end up proving that later on, but for now, I'll just say, and you're going to have to take me at my word for now, for the sake of time, that it doesn't matter what order you put these in, right? If I said 2x squared plus 2x plus 3x plus 3 versus what it is now, wouldn't matter, okay? So this order here of our B1 and B2 isn't going to end up mattering. All that we're doing in step 2, taking a bit of a break after the long step 1, all we're doing is we're just rewriting it out like this, okay? This is what we need to factor now, and you can see that if we just combine these like terms, we'd be back where we started there, right? The one thing that we can't forget, and I think it's really important that you guys see this. What did we pull out when we started? Yeah, all we pulled out was a 3. But that 3 didn't go away. Okay? That 3 didn't go away, so we have to be really careful that we rewrite it every time like this. Put the whole thing in parentheses, or I like to use brackets, right? So that I don't get confused later on. But I like to put brackets and say, okay, yep, that 3 we pulled out, that's still there, because that's going to end up changing really what your graph looks like. Okay? Okay, so now in step 3, all we're doing is we're taking those 4 terms and we're putting them in boxes, okay? So we have 2x squared, right? We have 2x squared, we have 2x, we have 3x, and we have 3. I'm just writing it like this to show you we have our quadratic terms, our 2 linear terms, and our constant, right? So between these 4, this kind of trick here, right, this way of solving things is going to work as long as we put our b terms in diagonal squares. Personally, I like to put our first term, right, our quadratic term, in the top left corner. This is traditional, I guess. But then, as long as these are diagonal, and really that's kind of plays into that same idea of the order of them didn't matter when we were writing them. But again, that's property of commutativity again that we saw way back in I think chapter 1. So we have 3x there and 2x; those are diagonal, and just 3. So we have 2x squared plus 2x plus 3x plus 3. Now all we end up having to do to solve this problem is just pull out our GCF from each column and each row. That gives us our set of factors. So let's just put a set of parentheses here. That didn't look that great for prints. Right? If these are a set of parentheses here, all we're doing is we're adding these 2 pieces together, whatever we pull out for GCF. So that's our GCF here in this first row. Well, it's not just 2. What else? Yeah, we can take out 2, but isn't there a variable piece? Yeah. So 2x. 2x plus what? We have 3x and 3. Proud of you. We got 3 there, and what do we have as our GCF out of this column? We have 2x squared and 3x, right? I think a really great way to think about this though too is to say, okay, yeah, now that I have one side done, and this will help you when you have some negatives built in, this is actually the best way to do it. If you say, okay, yeah, we have 2x times something equals 2x, right? Challenge yourself a little bit, and this will pay off even when you have like the really, really complicated ones with a bunch of negatives involved. So if we have 2x times something gives us 2x squared, what's that going to have to be? And for this problem, when we're dealing with all positives, you really are able to just pull out the GCFs there. So we have 3x and 2x squared. Thank you. We're going to have just x as our factor there. So what are we pulling out up top here? It's not nothing. What did I say before? See if you're listening now. What did I say before was going to be our GCF if we said that we had no GCF at all? It didn't change from the last time that we ever did GCF problems. What's the smallest your GCF can be? When something's unfactorable, what can you pull out no matter what? Thank you. Thank you. 1. So we have 2x plus 3 times x plus 1. It looks a little bit weird, but let's rewrite it out. We have 2x plus 3 times x plus 1, but I'm not done. What am I missing? Maybe I should write it first. Maybe you guys should write it first. Is it written on here? No, it's not written on here. 3. That's right. We have a 3 on the outside. So this is going to be our end result, right? We have 3 times 2x plus 3 times x plus 1, okay? This is really called factoring by grouping, but what we're using instead of something that looks really weird algebraically, we're doing the same beginning steps. So step 1's unavoidable. I'm sorry, guys. Step 1's unavoidable, but really using this step 3 instead of what the book says to use for step 3, this makes things a little bit easier, okay? So that slide I'm skipping is just the answers, but those will be back there for when you guys take a look at this later. So what were our steps here, right? We had our pre-check. Could we factor out anything? Yeah, we factored out from all three of our terms. We pulled out of 3, actually. Step 1, what did we do? We split b into 2 different linear terms, right? We split that b times x into b1x plus b2x, right? So we had a method for doing that, and instead, honestly, instead of taking factors of c that added up to b, we just needed factors of a times c that added up to b, okay? So it's a little bit more nuanced than what we had in that last section, but it'll help us do things that are a lot more complicated. Then we're taking those 2 numbers, instead of just plugging them into our factors and calling it a done day, right? We rewrite our problem with 2 b's. So we take that trinomial and make it, well, we don't really call things a quadrinomial, so we make that a polynomial, right? We give it 4 terms instead of 3, right? So from here to here, we're plugging in all of our terms into our grid, and then once we have our grid, we can just pull out the GCF from each column and each row. Again, if you have negatives involved, it's a lot easier to say, okay, what multiplies to get that square in there, and that's the best way of checking things. 2 is to just FOIL things out, right? Just like we did in the beginning of class, but that's going to give you your final factor form for whenever you have a trinomial that has a that isn't 1. Okay, so now we've done stuff where a is 1. It was a lot easier, and you can see, again, you can see as well that we need factors of b, or we need factors of a times c that add up to b. When a is 1, what happens? Yeah, this just goes away. So factors of c that add up to b, anything times 1 is itself. So when a is 1, this just goes away. So that's why it's easier to do it that way. And I'll show you guys a proof on the course page of why it actually works out that way, that you have to split it up and do the whole grid thing, why you can't just plug them in for the factors as well. But basically, no matter what, when a is 1, you can just plug those numbers in immediately, okay? So we have the practice problems now on that handout, and we'll walk through it just the same, okay? Go ahead and get started on that.